Okay, so hi everyone, and welcome to today's ABC seminar. So our speaker today is a PhD student at Warwick University under supervision of Theo Damoulas. Her mission is to better understand robust Bayesian inference and model misspecification, and how to apply this in health and medical sciences. She's here to share with us about this mission and about her recent paper published in ISTAT. So please welcome Harita Dellaporta.
Thank you very much for the introduction, for the invitation. So yeah, today I'm going to talk about this work which I did mainly on my first year of PhD, 1.5 first years, which was joint work with my supervisor, Theo, and Jeremiah Snodblouch and FX Brill from UCL. So the paper is Robust Bayesian Inference for Simulator-Based Models via the MMD Posterior Bootstrap. So a bit of outline of my talk before I begin. So I'm going to give you a bit of motivation on simulator-based models and the problem setting we're considering in this paper. Then a bit of necessary background on Bayesian nonparametric learning. And then I'm going to move on to the method, which is based on the MMD Posterior Bootstrap, and give you some theoretical results and a few examples at the end. So a bit of motivation. So when I talk about simulator-based models, I'm going to consider likelihood for inference setting, as I'm sure most of you are familiar with. So I'm going to consider models from which you can sample independently, but you don't have an analytical form of the likelihood function, either because it's unavailable completely or intractable. These models are interesting because in a lot of times they try to approximate some complicated phenomena that comes up a lot in natural sciences. So it could be a physical phenomenon or something in biology. And these simulators are usually a complicated series of equations, let's say, that try to give a good approximation of what's going on in the real data generating process, but it's likely that they are misspecified, so they can't always capture everything that's going on. So these are the two main problems we're trying to tackle. One is that we don't have the likelihood function, and the second one is that we want to take into account that our model might be prone to misspecification. So we don't want to make a standard Bayesian assumption that our model is true and then just set some uncertainty on the parameter of interest. So a bit more formally, so we're interested in parametric inference, so don't let the non-parametric learning framework confuse you here. So we're still interested on making inference for some parameter of interest theta that indexes our model p theta. And our model, as I said, is a simulator-based model, so it means that it's associated with a simulator function, sometimes also called generator function, indexed by the parameter of interest, and some Bayes measure U, from which we can sample from, is usually a probability measure we can sample easily from. So in order to sample independently from our model, we will have to sample from U and then map these independent samples through the simulator function g theta to get samples Y from the model. And we're also going to assume that we have observed some IID data that come from the true data generating process, which we denote by P star. And what we also want to make sure is that we don't make the assumption that P star is a member of this parametric family. So we're not going to make the assumption that there is necessarily some value of theta that will give me such a P theta will give me back P star exactly. So we're going to be in a misspecified case. So that's the problem setting, and our method is quite heavily based on what's called the Bayesian nonparametric learning framework and the posterior bootstrap algorithms that were introduced in a series of papers here by Lyddon, Fong, Chris Holmes, and Stephen Walkers in 2018, 2019. So I'm going to give you a bit of background on that first. So for a moment, we're going to forget a bit about the simulator-based models. We're going to leave the first problem that we don't have a likelihood aside and focus a bit on model specification. So the idea of these framework is that if we don't want to assume that our model is true, as we would do in standard Bayesian inference, we don't want to just simply set uncertainty on the parameter of interest theta for a prior, but we would like instead to place uncertainty directly on the data generating mechanism, which we denoted by P star, because that's the quantity that we're not sure about. So we want to place a prior, which in the case of this framework is a non-parametric prior, directly on the data generating mechanism. And we want to find a way to propagate this uncertainty from the data generating mechanism to the parameter of theta. So the authors suggest a Dirichlet process prior. So we denote this prior by P, and this is a nice choice that comes a lot in non-parametric statistics. One of the reasons is because there is it has a nice posterior conjugate posterior. Here we will denote with parameters alpha prime and f prime. And these parameters here in the prior have a nice interpretation, because as you can see, if our prior is centered around measure f, and the concentration parameter alpha here will dictate how much we believe in our prior. So f incorporates everything we already, all our prior beliefs about the data generating mechanism, if we have any. And then alpha will concentrate how much strength we want to set in these beliefs. And I said if we have any, because as you can see, if alpha here is set to 0, then this is like having a non-informative prior, because the posterior Dirichlet process is centered around this f prime measure, which is a combination, linear combination of the prior centering measure and our empirical measure after observing the data X. So here is clear that the larger alpha is the more we believe in F. So, so far we have a non-parametric posterior over the data generated mechanism after observing some data. But what we would like is to actually say something about the parameter of interest. So far the parametric model that we have assumed hasn't entered the picture yet. And we want to find a way to use this posterior beliefs about the data generated mechanism to make posterior inference about the parameter of interest theta. So with this idea in mind, if we have a loss function that, let's call it L, so that could be, for example, the negative log likelihood if that was available. What we would like is to propagate uncertainty from the data generating mechanism to theta. And our target would be the value of theta that minimizes the expected loss under expectation of the data coming from this true data generated mechanism. So this map says that if we did indeed know P star, if that was known, then what we would like is theta that minimizes this expected loss under P star. But in reality, we don't know P star, and instead we have a posterior distribution over this. So we want to use this map from the space of P star to the space of theta to make some posterior inference for theta. And this map basically defines a push forward measure from the posterior of P star to a posterior of theta. So mathematically, this corresponds to the push forward measure of the posterior through the map theta star, which is indexed by the loss function here. But it's good to note that this is not going to be the standard Bayesian posterior in theta. We instead call it the non-parametric learning NPL posterior in theta, because that's something different. It's just using the posterior of P star and this map that maps from the space of P star to theta to obtain a posterior relief on theta. So a bit of reminder, if you wanted a refresh of what push forward measure is mathematically, is this. But I think more interestingly, if you want to think about it in a more intuitive way, if we wanted to sample from this posterior theta, we would need to repetitively sample from the posterior of P star, which let's call it samples Pj. So that's the posterior Dirichlet process here. And then for each such sample, we can find theta that minimizes the expected loss, for which we will take expectation under the sample Pj. So that's what the push forward measure would be intuitively if we wanted to sample from this posterior for theta. And I will come back to this when I present the method, but just to have an idea of what this MPL framework essentially meant. So this was called the posterior bootstrap algorithm in these papers, because it's essentially a bootstrap of sampling from the posterior of the data generating process and then finding the corresponding parameter values that minimize the expected loss. So the idea is if we do this repeatedly again and again and you bootstrap, then your samples of theta will concentrate in the target value, which is the value of theta that minimizes the expected loss under the true data generating mechanism, which is unknown. So in a nutshell, this framework says that, okay, we don't want to assume our model is true, so we can set our uncertainty on the data generating process. And then by doing this, we're gonna bootstrap on its non-parametric posterior. So we have the non-parametric posterior of a P star in order to find values of theta that minimize expected loss for each subsample on the posterior of the data generating process. So now if we want to go back to our original scenario, so we said that we want this framework to be actually, so we want robustness, but we also want for this to be suitable for likelihood for inference. So what we suggested is that instead of having a loss function and minimizing an expected loss, we could also use this same framework, the same idea, but instead use a map that minimizes a distance between probability measures. So we can use a distance-based loss function, essentially. This is all it is. And our target now would look like minimizing distance between the parametric model family and the data generating process. So again, here we have if we have our targets. If we knew P star exactly, then this would just be a minimum distance estimator. With minimum distance estimators, just a frequentist approach, which is based on minimizing distance between probability measures. So essentially, our target here is now indexed by the distance that we choose. And again, if we wanted to find the NPL posterior for theta in exactly the same way, we can define the push forward measure of the posterior of P star through this map. So again, we would have the Dirichlet process posterior of P star, and then this map will define the values of theta that minimize distance between each of the samples from the posterior and the parametric model. So now comes the question of what distance should I choose? So of course, we want something that works for models that we don't have a likelihood for. And we'd also like to have some robustness guarantees of the distance measure itself. So similarly, as in a lot of likelihood for inference methods, you would like to choose a distance measure that has robustness properties in the same way that you would use them in just a minimum distance estimation. So what we suggest is that MMD, as you probably have guessed by the title of the paper, so that's the maximum mean discrepancy. And by using this measure of distance, which I'm going to explain in a bit more detail, what we have as the map theta star is now a minimum MMD estimator, which such estimators have been explored in the literature quite a lot. So, for example, first in this paper by in 2019 by Briol and co-authors, and later also its finite sample properties of these estimators were explored quite extensively in this paper by Harita Dellaporta and G-and-k. And Pierre also talked a little bit about this in his last month's talk. So our theoretical results of our methods were quite a lot based on this paper and the corresponding results. So it was very useful for our work. Okay, so let's take a break and actually say what the MMD is. So MMD is an integral probability metric. So these are metrics which restrict functions in a class of functions F. So we restrict the class of functions we're considering, and we look at the supremum of the difference of the expectations of these functions under each of the two probability measures. So it kind of looks at the worst case scenario of how far away can these expectations go in this class of functions F. And for different choices of F, we have different IPMs. And of course, depending on the choice, this could or might not be a probability metric. So MMD is an instance of an IPM where we restrict this class of functions to be a unit reproducing kernel Hilbert space, which is a space which is defined through a kernel function. And the nice thing about this space is the reproducing property, which allows you now to write the functions in this space through inner products and only using kernel functions. So computationally, from a computational side of view, the MMD is quite nice, because if we restrict now F to be this RKHS, a unit one, so we also restrict the norms in this space of the functions to be upper bounded by 1, then it's been shown that we can write the squared MMD like using these double integrals, so just expectations of kernels. So what happens is that we don't have to now compute this supremum of the functions, and we have something which is a lot more easy to approximate. And of course, this can be approximated through simulation, through sampling from P and Q and calculating these kernels. So it makes it quite suitable for likelihood-free inference. So one of the examples of estimators of the MMD is the U statistic, which we also use in our method, which is just an unbiased estimator of the squared MMD here. So we would need, in our case, the samples from P and Q in order to estimate this MMD. So a computation is very nice, it's suitable for likelihood for inference. And also in the papers I mentioned here, it was shown that these minimum MMD estimators have some really nice robustness guarantees. So in a sense, we using this measure of distance between probability spaces in the MPL framework kind of gives us we have a twofold source of robustness in the method, because one is the MPL framework on its own, because that framework does not make this huge assumption that the model is true. And at the same time, we have a distance-based loss function, which is on its own, has nice robustness guarantees, which I'm going to come to when I talk about theoretical results. But it's also more reliable in cases where we could have misspecification or outliers and stuff like that.
So how sensitive would that be with respect to the kernel you choose?
Yeah, of course. Yeah, I would come to that as well.
Okay, sorry.
Yeah.
Sorry. Thanks.
No, it's a good question. So of course, as in all kernel methods, like the kernel is maybe the biggest limitation. So of course, your whole objective function here would change if the kernel changes. So it's harder to tune. And that's something that, yeah, is true in all these MMD estimators and kernel methods. And it is also true here that it would change your objective functions completely, essentially. But yeah, I'll come a bit more to that in a bit. So yeah, so if we go back to the MPL frameworks now, what we have here is that our target essentially would be the value of theta that minimizes this estimated essentially MMD between the true data generating mechanism and the parametric model. And we would like to now go back to how would we actually use the non-parametric posterior of P star to sample from the posterior MPL posterior of theta. So I remind you, P star is a true data generating mechanism, and we have this non-parametric posterior adversarial process of a P star. So if we wanted to sample from the posterior of theta, again, we're going to use this posterior bootstrap algorithm that I briefly mentioned earlier, which we call MMD posterior bootstrap simply because we have the MMD based loss function. So a little bit of a small illustration of what I was saying earlier. So what we want is to sample from the posterior of the data generating process. So we have independent samples, for example, here, P1, P2, P3. And for each such sample, we can map this to the value of theta that minimizes the MMD between this sample and the parametric model family.
Can I ask a question? There's something I don't understand. So you're using this sort of empirical version of the MMD squared by this U statistic. So when you do that, are you sampling from P theta and then you're taking an empirical version with the sampler? And then what does it mean to minimizing theta? Or are you just sampling from Pj? And I didn't get it.
Yeah, I think, it's a good question. So what we want to do is minimize the MMD. So we use this U estimator to perform some sort of numerical optimization. So in practice, if we use a gradient-based optimization method, you would use a similar U statistic for the gradient of the squared MMD here and sample both from P theta and Pj to find your gradient and update theta in a sense. So that would just be your objective function. So in reality, I guess you would use the gradient of the U statistic of the gradient of the MMD to perform some gradient-based optimization. But if you use some other form of optimization, you could estimate this first and then perform it. But that's in practice, that's what we did. So we sampled both from Pj and P theta, estimate the gradient, and then update theta. Does that answer your question?
Yeah, it should be like some kind of SGD or something.
Yeah, exactly. Something like SGD, yeah, or ADAM or any sort of numerical optimization, yeah. And yeah, I'll get to how you sample from the adversarial process now in a second, and then sampling from P theta will be through the simulated base function that I said in the beginning. So through that map G theta. Okay, yeah, so this bootstrap algorithm means that for each sample I have from my posterior here, I have a new objective function that I minimize. So I find theta that minimizes this MMDs for samples around the posterior of P star. And each of these samples are independent from the other in the sense that I don't use any information from theta 2 to find theta 3. So that's why the algorithm becomes parallelizable, because each pair of these two steps can be done in parallel. So you don't need to do this, that they don't have any sequential dependency in that sense. So computation is quite nice. So what essentially we would like is that if we do this again and again, and we have a lot of bootstrap samples, they will eventually, these thetas will concentrate around the minimizer of the MMD between the true data generating process and the parametric model family that we have. And I did talk briefly about the approximations here on MMD. But there is also an approximation happening here, of course, because we can't sample from the data process exactly. So here we follow a similar, the same actually, suggestion as in the NPL framework papers, which is a way to approximate this digital process measure. So I guess the most usual way that people would approximate this is through the stick breaking process. If you're familiar with it, if not, it's okay. But this is just another type of approximation, which is done through digitally distributed weights. So in order to approximate these samples, you would have to sample from the prior centering measure of the digital process. So these X tildes here would encode how much, essentially all our prior beliefs about P star. And alpha dictates again how much we believe in those. And then we combine these pseudo, let's call them pseudo data, with our observed data through weighting by the Dirichlet distribution. So each of these samples in practice, it will look like this. So sampling from PJ is quite straightforward. And here in new hat, we will just denote this approximated, posterior measure. Okay, so the algorithm, again, if you want, is essentially comes down to these two steps. So that we have the sampling step, which is sampling from this approximated Dirichlet process measure. And this would be a sample of posterior on the data generating process. And then for each of these samples, we then use some sort of numerical optimization to obtain the value of theta that minimizes the MMD between this sample and our parametric model. And I guess, yeah, again, this is maybe a little bit better illustration of what's going on. But again, yeah, here in practice, as we said earlier, if we're using a gradient-based method, we'd come down to estimating the gradient of the MMD, or that also depends on the generator function. So of course, if you have something very complicated, it might come down to doing some sort of auto differentiation. But what you would like is be able to minimize this MMD. And of course, yeah, this will depend on the kernel. So yeah, a very usual choice, for example, in the literature is the Gaussian kernel, which satisfies some assumptions necessary in the theoretical results I'll come to. And there is how you would tune that kernel, its hyperparameters is an open problem in a sense, because there are some heuristics in the literature that we used as well, but you don't have a guarantee that these heuristics will work. So, for example, there's a median heuristic that's based on the median of the data, and there is also a suggestion to use a weighted combination of Gaussian kernels, which we also use. So you don't just choose one kernel, but you choose a combination of loads of kernels. But it is indeed, this is not something that's completely solved in a way, or you have some sort of guarantee on that. So we also use this sort of suggestions that already existed in the literature. Okay, so let's have a little bit of look at the theoretical results I mentioned a bit earlier as well. So we started by generalization error of the method. So first of all, one assumption that we make here, following the assumptions essentially needed in these results from MMD estimators, is that the kernel is bounded. So here, without loss of generality, in these results, I'm using an upper bound of 1, but we need, in any case, we need the kernel to be bounded above, so and below. So here, what we care about for the generalization error is essentially this quantity. So this is the expected error, which in terms of the MMD. So error in terms of the MMD between the true data generating process, and here P, the model, P theta, indexed by parameter theta star of P. So here theta star of P, I remind you, is just the theta that minimizes the MMD between P, so sample P, and the parametric model family P theta. So that's why here we have indeed a double expectation. So we have expectation because we have a finite sample from P star, and we also have expectation over the fact that P is a random sample from the posterior of P star. So just a little reminder, the notation gets a little bit confusing here. Nu hat is just the approximation to the Dirichlet process. So we actually do have the same results hold similar results. Oops, sorry, a spoiler. So the same results hold for the exact Dirichlet process, but we also show them for the approximation, which is probably a bit more interesting because it shows that this approximation doesn't really break down anything, essentially. So here, of course, the expected error is trivially lower bounded by this infimum of the MMD if we are misspecified. So if we go back to the original picture I showed you, so we don't make this assumption that P star is a member of the model family. So there is the best thing we can do is this infimum of the MMD between our parametric family and P star. So we would like essentially our error to, if we get more and more data, to tend to this lower bound. So exactly what we care about is the difference between this expected error and the infimum of the MMD here. And what we upper bounded by is these two terms. So of course, this would vanish to zero if we get enough data, and the overall rate of this decay would be dominated by this first term here. So it will be of order 1 over square root of n, which it agrees is the same type of rate that we see in these results that were also presented by Pierre last time. So this rate will agree here with minimum, the usual robustness guarantees of the MMD. Because this term will actually decay faster. And just a little reminder that this will essentially come through because of this alpha parameter of the Dirichlet process. So this is not extra, like we can say like an extra term, but it will actually decay faster. That's the idea. So that's a nice upper bound we have here, and we can actually use that to show some sort of posterior consistency results that we would also like to have for our NPL posteriors. So here things are a little bit different than one would imagine. So if we think about, if we assume we have a standard Bayesian posterior for theta, so let's call it like pi n. We don't have that, but what we were meant to say is that if we had that, the result we would like would look a bit like this. So we would like our posterior on theta to go to zero as we get more and more data for values of theta that induce large values of MMD. So as we get more data, this also goes to zero. So the posterior will concentrate in smaller and smaller neighborhoods around values of theta that induce small values of MMD. So this is what a standard Bayesian, a standard posterior consistency result will look like. But we don't really have a posterior directly in theta. So as we said, our posterior in theta is indirectly defined through this map theta star. So instead, what we will have, the result we have is a similar result, but it's actually based on the posterior of the data generating mechanism P star. So here again, this would work both for the approximation and for the exact case. But here for the approximated posterior in P star, we have essentially the same result. So we want this to this posterior to concentrate around smaller and smaller neighborhoods of values of P that give essentially induces small values of MMD, so values of MMD close to the best case scenario, where here we have indirectly the values of theta defined through the map theta star p. So all it's saying is using this map, this will concentrate to the values of p that we want, that gives you the values of theta close to values of theta that induces this infimum of the MMD via this map. So that's the posterior consistency that we have here. And a last theoretical result here is, again, is similar to the results in Badger's and Pierre's paper. So here we consider a specific case of model misspecification, which is Huber's contamination model. And we consider this both because, you know, it comes quite often in real life, and also because we also actually use this kind of examples in our applications as well, because it's just a model that's quite easy to check if you're actually doing well or not. So it's easy to assess how the method is doing. And so here we consider that our true data generating process is a combination of p tilde, which is a big proportion of data coming from p tilde, which is what we would like to come close to, and a small proportion of data coming from some distribution Q. And we show a similar result to our generalization error. So now we look at the expected error between p tilde and our estimated model. And here we see that essentially we have this extra term here, which comes from the level of contamination. And what this shows is that essentially if the level of contamination does not dominate this term here, then we would recover the same rate we had in the general case, no matter what Q is. So no matter how far away Q would be from p tilde, no matter where the outliers are, as long as the level of contamination is not too big and that doesn't dominate with respect to how much data we have, then we'll recover the same rate. So it's this type of guarantee. Okay, and now let's have a look at like such an example, for example, a contamination model. So here we just consider the G&k distribution, which I'm sure most of you are familiar with. Is quite well studied in the likelihood for inference literature. And here we would actually consider a contaminated model. So what we have is that the model is actually, so data comes from the G&k with parameter theta naught. So that's how data from the G&k distribution looks like. And we will also add some outliers, so some contaminated data to the left and right of this data. So that's what P star would look like with 10% of outliers, for example. So this is a small illustration. So essentially what we would like is to get a posterior estimate for theta. So using our method, we will get a posterior bootstrap sample. And then if we get an estimate from that, let's say a posterior mean estimate, then if we use our value of theta to sample from the G&k, we would like the data to essentially come from something close to p theta naught rather than get influence from the data from Q. That's the goal in this contaminated models. So in the paper we have compared with a few methods, so both some ABC based methods, as it's most popular, I guess, likely for inference methods, and some GBI methods as well. Here I only have a few, like just an illustrative example. So one of the methods we compared against, we used was the ABC method based on Wasserstein distance. So here we just sampled like 500 samples and just took the mean estimate. And we see this is also with our method, just a bit how the data would look like when we sample using the estimate for theta. And just this is, I think this is a bit better illustration. Essentially here we just plot the posterior marginal densities for each of the 4 parameters, just with a bit of reparametrization. So we have the bivariate densities and the univariate ones. And the dotted lines here just indicate how where the true parameter value lies. So as I said, it's in a contamination model, you can pretty much tell where you want your theta estimates to concentrate around. So your posterior for theta. And from left to right, we have an increasing level of contamination. So here we just see where exactly our posterior concentrates. And I think the idea is that because a standard Bayesian posterior also can be prone to misspecification, because this MPL framework essentially does not try to approximate the standard Bayesian posterior. So the goal is not to find come close to where the standard Bayesian posterior is, but the goal is to concentrate around the values of theta that will minimize this MMD between the true data generating process and your parametric model family is less prone to misspecification. That's a bit like how, but of course you can see how, not all bootstrap samples will come exactly where you would like them to be. So for example, here is quite clear, but what you hope is that if you get enough bootstrap samples, they will concentrate around this minimizer of the MMD, or a minimizer if it's not a unique one. And yeah, speaking about this, I didn't mention this earlier. So when I was talking about the MMD, so in the theoretical results, we didn't need to make the assumption that the kernel is characteristic. So if the kernel is characteristic, that would make the MMD a metric, so meaning that it would be 0 if and only if P will be equal to Q. So that's not something we need for the theoretical results, but it would be something that we would like to have in practice, because if we wanted to, in the well-specified case, to recover the true data generated mechanism, we would need that the characteristic of kernel. So that's something that we would desire in practice. And we also consider this toggle stitch model, which perhaps a little bit more interesting. So this is a model that comes in biology. It describes the interaction of genes over time. And this is a simulator, just to prove to you that there is likelihood for inference model. So it's a bit more complicated, as you can see. So of course the simulation is also a bit more expensive because it's still a one-dimensional output, but the latent dimension here, t is of the order of 300. So the latent dimension is something like 600. So this model has 7 parameters, and we have just a similar illustration of the posterior marginal densities when we add Cauchy distributed noise to 10% of the data. So this is what the data looks like from this model. And of course, here again, it's these 2 examples that I've put here are both as a form of Huber contamination model. It's of course harder to assess in real life how you would actually do if you had a different model specification. So if your model family was completely different with the true data generated mechanism, that's what you would like in practice. It's just it's harder to assess. We have some toy examples with, like, for example, fitting like a normal distribution to Cauchy distributed data and something like that. But that's just a few illustrations I put here. And if you are interested, we have more comparisons as well. This is just to show you a bit how our method is doing in these two examples. And yeah, before I stop, I think, yeah, as I did briefly mention this, of course, I think the biggest limitation of the method would be the optimization. So there is a numerical optimization involved here, as in a lot of these kernel methods, which of course is not something that you can guarantee you can find a minimizer for if your objective is not convex. And there are quite a lot of cases where depending on your model, that the MMD objective will not be exactly convex. So I think for sure, if I would say where I would look after this, potentially some guarantees on the kernel constraints on the kernel to make this objective behave a bit nicer, or have some sort of guarantee in your optimization would definitely be desirable. For the moment being, yeah, we use this MMD distance-based and existing tools for the minimization of this objective. And yeah, I think that's all I had to say. Thank you very much for listening. I got some references here, and I'm happy to get any questions you may have.
Thank you.